Getting directions from point A to point B is the most known use of GPS. However, GPS has many more applications. Precision farming uses GPS. Airplanes use GPS to help them land smoothly. Emergency crews use GPS to find people in need of their help. Almost everyone has used GPS, but few know the science and math behind it.
How does GPS work?
GPS uses satellites to find location. The distance from the satellite to the receiver is calculated by using delta D equals V delta T. The satellite sends radio waves traveling at the speed of light to the receiver, while an onboard atomic clock calculates how long it takes for the signal to return. 4 satellites are then able to use distance to find an accurate location. For example, say I am trying to locate this plane. If the pink satellite was 20,221 kilometers away from the plane, then I would know the plane would be somewhere on the edge of the circle. Suppose the yellow satellite is 20,219 kilometers away from the plane. Now, there are 2 possible locations. A third satellite improves accuracy. Now the location of the plane is obvious.
I thought 4 satellites were needed to find our location.
Yes. While only 3 satellites are needed on a 2D model, when you add a dimension, you must also add a satellite. There are many factors affecting GPS, including the rotation of the Earth and the elliptical orbits of the satellites. The most interesting factor of all is relativity.
Sounds fascinating. What is relativity?
In science, relativity often refers to Einstein's theories of general and special relativity. In his theory of general relativity, Einstein predicted that objects with large masses are able to curve spacetime. The spacetime is distorted when a heavy object is placed within it, much like standing on a trampoline.
It's mind-blowing.
Because of this, time moves faster as the clock gets further away from a gravitationally intense object.
Is that why the laundry in the basement seems to take so long when I'm up in my room?
While the effects on Earth are too small to measure, I believe you have the right idea. Now we can move on to special relativity. Suppose the spaceship, which is traveling at half the speed of light, decides to turn on its headlights. From a stationary frame of reference, you may say that the light is traveling 1.5 times the speed of light. That, however, cannot be true because the speed of light is a constant in the universe. When it is solved, velocity comes out to be greater than the speed of light. In order to keep velocity at the speed of light, distance and time must be distorted. Special relativity shows that objects moving at high speeds experience time slower. The satellites are affected by general relativity because of their distance from the gravitationally intense Earth. Since the satellites are moving at high speeds, the effects of special relativity also apply. With the combined effects, the atomic clocks onboard the satellites are ahead by 38 microseconds per day. If GPS didn't account for relativity, then time would be incorrect, thus resulting in an incorrect distance. Without an accurate distance, then finding the correct location would not be possible. You may be tempted to roll your eyes in disbelief at Einstein's theory of relativity, but just remember, every time you use GPS, you are helping to confirm Einstein's theories.